everybody, in this video we're going to use the model of thermodynamics to calculate some interesting quantities for some interesting processes. In this example we have a gas that's expanding. It starts at point 1 and then expands to point 2. We want to figure out three things. We want to figure out the heat that is transferred to or from the gas during the process, the work that is done on or by the gas during the process, and the change in internal energy for the gas. We're going to start with work because it's the easiest thing to find with a PV diagram. With a PV diagram, work is just the area under the line. So in order to calculate the work done during this process, we just have to calculate this area. This may require you to think back to geometry where you learned about the areas of various shapes. There are two ways that we can calculate the area for this shape. We can either think of it as a trapezoid or think of it as a rectangle sitting beneath a triangle. I'm going to use that second way. Let's start by calculating the area of this rectangle. The area of the rectangle is just the length of one of its sides times the length of the other side. The quote-unquote height of this rectangle is just equal to the pressure of the gas at this point. I've actually given us some numbers to work with. The pressure at that point is 100,000 pascals. And the width of this rectangle is just the difference in volume between this point and this point. Our first volume is 2 times 10 to the negative 2 meters cubed. And our second volume is 5 times 10 to the negative 2 meters cubed. So our area for this rectangle is just equal to 100,000 pascals multiplied by that difference in volume, which is 3 times 10 to the negative 2 meters cubed. If we plug this into our calculator, we should get a value of 3,000 joules. Now let's do the same thing for this triangle. This triangle has the same width that the rectangle had. It's just the difference in volume between this point and this point. To calculate its height, we just have to calculate the difference in pressure between this point and this point. We know that the pressure at this point is the same as the pressure at this point. It's just 100,000 pascals. And we know that the pressure at point 2 is just equal to 200,000 pascals. So the height of this triangle is equal to 100,000 pascals. So we have a height of 100,000 pascals, a width of 3 times 10 to the negative 2 meters cubed, and we know that the area of a triangle is these two numbers multiplied together and then divided by 2. So we have 100,000 pascals times 3 times 10 to the negative 2 meters cubed times 1/2, and this equals 1,500 joules. So our total work is just these two numbers added up. It's 4,500 joules. But is this work positive or negative? Well, we know that positive work is done when the volume of a gas is decreasing, because in general, work is equal to the negative pressure times the change in volume. In this case, our volume is increasing, so we know that the work being done must be negative. So we've got one done. We found work for this process. Now we're going to calculate the change in internal energy. Now you might be looking at this diagram and saying, I don't see how we can possibly get information about the internal energy from this diagram. But it turns out we can, and I'm going to show you how. What do we know about the internal energy of a gas? Well, we know that gases do not have bond energy. The particles in a gas are free to move around on their own. So when we're talking about changing the internal energy for a gas, we're actually talking about the change in thermal energy for the gas. In order to find that, we need to know a couple of things. First off, we have to remember what thermal energy was in terms of properties that we might be able to calculate in this problem. We found in a previous DL that the change in thermal energy for 1 mole of a gas was just equal to 1/2 times the number of modes per particle times R, the ideal gas constant, times the change in temperature. We're going to assume that this is a monatomic gas, meaning that the number of modes per particle is just 3. R is the ideal gas constant. We know that. But what about delta T? How can we find that from this information? Well, here's the question that we need to ask ourselves. Do we have enough information in this problem to calculate the temperature at these 2 points? The answer turns out to be yes. We need one more equation, though, in order to do this. It's the ideal gas law. The ideal gas law just says this: the pressure of the gas multiplied by its volume must equal the number of moles times the ideal gas constant times the temperature. But for this gas, we have all of these numbers except the temperature. We have pressure, volume, the number of moles, and the ideal gas constant. So we can just calculate the temperature for these 2 points. Let's just plug in the numbers. So for point 1, we use the first pressure and the first volume. So we have 100,000 pascals times 2 times 10 to the negative 2 meters cubed is equal to the number of moles times the ideal gas constant times the temperature, which is what we're trying to find. Plugging all these numbers in, we get that the initial temperature is equal to 240.6 degrees Kelvin. Now let's do the same thing, but with state 2. Now the volume is 5 times 10 to the negative 2 meters cubed, and the pressure is 200,000 pascals. Plugging all this in, I get that temperature 2 is equal to about 1,203 Kelvin. But now we have actually all the information we need to determine the change in internal energy. We know the number of modes per particle, it's 3. We know R, it's the ideal gas constant, 8.314. And we know delta T. Delta T is just the change in temperature. It's about 962 degrees Kelvin. So now let's just plug these numbers in to find out what the change in thermal energy is. Plugging these numbers in, I get that the change in thermal energy is equal to about 12,000 joules. So now we've found delta U, and the only other thing we need to find is Q. But we actually know that there's a relationship between delta U, Q, and W. It's just conservation of energy. The change in internal energy is equal to the heat that enters or leaves the system, plus the work done on or by the system. We now have 2 of those numbers, so we can just write down that equation to find the third. And if we solve this for Q, we just get that Q is equal to 16,500 joules. And there are our answers. Heat is 16,500 joules. Work is negative 4,500 joules. And delta U is equal to 12,000 joules. Let's do one more example that's similar but has some key differences. This example starts out looking exactly like the first example. The process from 1 to 2 is the same one that we just did. But now we're extending it. Instead of stopping at 2, this process now continues around this loop to point 3 to point 4 and then back to point 1. The questions that we want to answer for this problem are the same ones that we wanted to ask in the previous problem. How much heat do we have to add or subtract from the system? How much work has to be done on or by the system? And what is the change in internal energy? In this example, we're going to actually start with the change in internal energy. It turns out that for processes that go in a cycle, in other words, processes that start and end at the same place, the change in internal energy is incredibly simple to find. Think about it for a moment yourself. What is the change in internal energy? Well, we know that internal energy is a state function. It only depends on the state that the gas is in. But what do we know about our beginning state and our ending state? Well, they're the same state. We're both starting and ending at point 1, which means the value of all state functions must be the same at the beginning as it is at the end. So our change in internal energy for this process is just 0. We're starting and ending at the same place, and so we're starting and ending with the same amount of internal energy. So now we just have to find work and heat. The fact that the change in internal energy is 0 makes this quite straightforward. We have the conservation of energy equation, but we know that the change in internal energy, also known as the change in thermal energy for a gas, is just 0. So this immediately tells us that heat and work must be equal and opposite. We know how to calculate work on a PV diagram. We just have to calculate the area under each of the individual processes. But there are some things that we can think about that will allow us to simplify this down. First off, look at the process that takes the gas from point 2 to point 3 and the process that takes the gas from point 4 to point 1. What do you notice about these processes? Well, they're vertical lines, which means they're happening at constant volume. Any process that happens at constant volume does no work, because we know that work is equal to the negative pressure times the change in volume. So we don't need to even think about those two processes when we're calculating work. However, there is work done during the process that takes the gas from point 1 to point 2 and the process that takes the gas from point 3 to point 4. Now, one thing we could do is calculate the area under these lines separately, but it turns out there's a simpler solution. Whenever you have a cycle like this, one piece of your cycle will always result in positive work, and one piece of your cycle will always result in negative work. In this case, the process that takes our gas from point 1 to point 2 does negative work, and the process that takes our gas from point 3 to point 4 does positive work. So these two processes will always cancel out partially. What will be left over? Well, for a cycle, it turns out that what's left over is just the area inside the shape. So all we have to do to calculate the work done is calculate the area inside this shape. I've drawn this as a parallelogram to make calculating its area easy. The area of a parallelogram is very similar to the area of a rectangle. It's just equal to its height multiplied by its width. In this case, the height of our parallelogram is this distance, which is the same as this distance. That distance is the change in pressure between point 4 and point 1. I've given us more information. Pressure 4 is 300,000 pascals, and pressure 1 is 100,000 pascals. That's a difference of 200,000 pascals. So the height of this parallelogram is 200,000 pascals. What about its width? Well, its width is actually this distance here. We're not taking the length of this line, we're just taking the width. You can think of it as being the horizontal piece of this line here. Well, what is this width? It's just the difference in volume between point 1 and point 2. That difference in volume, we already know. It's 3 times 10 to the negative 2 meters cubed. Multiplying this out, we get that the work done is equal to 6,000 joules. But we have to ask ourselves the question again, is this positive work or negative work? To do that, let's just think about the two processes that are doing work. This first process, we already know, does negative work because the volume is expanding. This process above it does positive work because the volume is contracting. But which one does more overall work? The answer is this upper process, because there's much more area under this process than there is under the lower process. So we expect that the positive work done by this upper process will be greater than the negative work done by this lower process. And so this number should be positive. There's an easy rule to remember whether work being done is positive or negative for a cyclic process. You just have to look at the direction that the process is going. In this case, our process is going counterclockwise. Whenever the process is going counterclockwise, the work done will always be positive. If we flip this around and sent it the other way, the work done would be negative. So now we just need to know what the heat is. But because the change in internal energy is zero, we know that heat and work are just the opposites of each other. So now that we've found work, it's very easy to write down heat. So this process is gaining energy in the form of work and losing energy in the form of heat. The amounts of these are exactly equal, and so the total change in internal energy is just zero. Next DL, we're going to continue talking about one of the ideas that we introduced in this DL, the idea of microstates and probabilities. This may seem a little abstract to you, but it turns out to be incredibly useful in physics, particularly when we're talking about the large numbers of particles that we typically find, say, in a gas. And we'll see how that's useful next time.